Welcome to the next lesson in the Dirty Medicine Biochemistry series. In today's video, we're going to talk about something called oxidative phosphorylation. This is probably better known as the electron transport chain. When we left off, this is what we had discussed so far. Glucose can undergo glycolysis to become pyruvate. Pyruvate can also go back up to glucose through gluconeogenesis. Pyruvate can take one of four metabolic pathways. The most common destination for pyruvate is to be turned back into acetyl-CoA. Acetyl-CoA can then go through the TCA cycle, also known as the Krebs cycle, to generate NADH and FADH2. When we had left off, I told you that these were incredibly important byproducts, and this video today will explain why. NADH and FADH2 will go on to be used in a set of redox reactions that transfer electrons in oxidative phosphorylation to generate massive amounts of ATP. So in today's video, we're going to talk about oxidative phosphorylation, also known as the electron transport chain. And by the end of this video, you'll understand everything that you need to know about the electron transport chain, including how electrons are shuffled through the chain, how the ATP synthesis works using a proton gradient, and how different electron chain inhibitors inhibit various parts of the electron transport chain. We'll close the video by talking about the total ATP production in all of these biochemical pathways so that you can keep the big picture in mind. With that said, let's get started. The goal of the electron transport chain is to couple energy stored in electron acceptors to a proton gradient that drives ATP synthesis. This will become much more clear as the video moves forward. To get started in this video, we need to design the electron transport chain so you have an image in your brain as to how this actually works. What you see here is the inner mitochondrial membrane in the middle of the slide. The bottom portion of the slide represents the mitochondrial matrix, and the top represents the intermembrane space. Now, along this inner mitochondrial membrane, we have a series of complexes, shown here in various colors. These complexes are numbered from 1 to 5. Complex 1 is shown in blue, complex 2 is shown in light pink, complex 3 in light green, complex 4 in that peach color, and complex 5, which is better known as ATP synthase, is shown as the gray triangle on the far right. Additionally, you have the presence of two other molecules that act not as complexes, but they are embedded in this area of the electron transport chain. Those are coenzyme Q and cytochrome C. So CoQ and cytochrome C, shown there in the darker salmon color. Now technically, these are broken into two distinct parts of oxidative phosphorylation. The complex portion from 1 to 4, including CoQ and cytochrome C, is known as the electron transport chain, because this is where electrons get shuffled from one complex to the other. The ATP synthase, which pumps the proton gradient to generate ATP, and again we'll talk about that at the end of the video, is technically known as chemiosmosis. Now it's the combination of the electron transport chain plus chemiosmosis that is together known as oxidative phosphorylation. That distinction is probably not important for the purposes of exams, but for keeping the big picture in mind, you should know that when somebody refers to oxidative phosphorylation, they're referring to this entire process. But when somebody refers to the electron transport chain, they're technically only talking about the movement of electrons from complexes 1 to 2 to 3 to 4 to oxygen, but they're not actually talking about the final ATP synthase pump that generates the ATP. Now, how this works is the complexes exist in the membrane, and you have protons that are in the mitochondrial matrix. I told you that when we discussed the TCA cycle, the goal was to produce NADH and FADH2 for use right here in the electron transport chain. So let's illustrate why those molecules are so important. So along comes NADH, and NADH approaches complex 1. NADH can give up its proton and give up its electrons and become NAD+. In the process, it donates its electrons to complex 1. When the electrons enter complex 1 gets supercharged, illustrated here with the yellow fuzzy border. When this complex gets supercharged, it has the energy to pump the proton from the mitochondrial matrix into the intermembrane space. As it does this, it pumps more and more protons from the mitochondrial matrix into the intermembrane space, and you get the accumulation of protons on the other side of the membrane. This goes again from the mitochondrial matrix to the intermembrane space, but this pumping is only made possible by the electron given up from NADH supercharging complex 1. Now, after a while, the electron will sit in complex 1 and the proton gradient is beginning to form. On the top, in the intermembrane space, you have much more protons than exists on the bottom in the mitochondrial matrix. Now, at this point, the gradient is beginning to form and complex 1 will pass its electrons to CoQ. The electrons will go to CoQ and sit there awaiting further instruction. Now, at this point, FADH2 comes along and approaches complex 2. Just like NADH, FADH2 was produced in the TCA cycle. It migrates here and begins its important role. FADH2 can give up its electrons and turn into FAD. In this process, it donates its electrons to complex 2. Complex 2, however, cannot become supercharged and cannot pump protons from the mitochondrial matrix into the intermembrane space. So the electron sits in complex 2 and awaits further instruction and ultimately gets passed to CoQ. Now I want to pause for a second. NADH only works at complex 1. FADH2 only works at complex 2. So the electrons given up from NADH go from 1 to CoQ, and the electrons given up by FADH2 go from complex 2 to CoQ. Now, it's important to pause and understand something that's very high yield. CoQ is the common electron acceptor from both complex 1 and complex 2. It's also incredibly important and very high yield to remember that NADH only gives up its electrons at complex 1, and FADH2 only gives up its electrons at complex 2. At this point, the electrons are sitting in CoQ and they are passed to complex 3. When the electrons go from CoQ to complex 3, it supercharges complex 3, which creates enough energy potential to pump the proton from the mitochondrial matrix through complex 3 into the intermembrane space. Just like we saw when complex 1 was supercharged by the electrons coming off of NADH, complex 3 is being supercharged by the shuffling of electrons both from complex 1 and complex 2 to CoQ to complex 3, supercharging it and helping to create this proton gradient. Look at the slide. In the intermembrane space, you're getting the accumulation of protons. There's a much greater positive charge on the intermembrane space than there is in the mitochondrial matrix. So we're continuing to form a very big proton gradient. At this point, complex 3 will pass its electrons on to cytochrome C. At cytochrome C, the electrons arrive and then get passed to complex 4. At complex 4, the electrons enter it and supercharge it, just like we've seen in complex 3 and in complex 1. Once supercharged, complex 4 has enough energy to pump protons from the mitochondrial matrix into the intermembrane space. Again, the proton gradient continues to form. Look at the top of the slide. The intermembrane space is laced with tons of positively charged protons. So there's a proton gradient compared to the mitochondrial matrix, which has fewer protons. At this point, complex 4 has the electron sitting inside of it, and it needs to pass to the final electron acceptor. The final electron acceptor is oxygen. The electrons are passed to oxygen, which splits into 2 oxygen ions, and protons are added, creating 2 water molecules. Let's pause for a second. It is incredibly high yield to understand that the final and ultimate electron acceptor in the electron transport chain is oxygen. And by accepting the electrons and accepting protons, 2 water molecules are formed. Everything that I just said in that sentence is incredibly important and high yield to keep in mind when you're taking exams. Look at the electron transport chain. Complex 1 and complex 2 pass their electrons to CoQ. CoQ pass their electrons to complex 3. Complex 3 pass their electrons to cytochrome C. Cytochrome C pass their electrons to complex 4. and complex 4 passed their electrons to the ultimate electron acceptor, oxygen, which split into 2 oxygen ions before forming 2 water molecules. Everything that I've just said is the electron transport chain. And at this point, the electrons have been shuffled from one complex to the next, supercharging the square complexes that you see here, which are complexes 1, 3, and 4, to pump protons from the mitochondrial matrix into the intermembrane space. Now at this point, we've formed a massive proton gradient. There are so many protons in the intermembrane space and so fewer protons in the mitochondrial matrix. Now it's at this point that ATP synthase comes into play. ATP synthase is going to make use of this proton gradient to generate massive amounts of ATP. So along comes the molecule ADP, and ADP wants to turn into ATP, which is a higher energy molecule that can be used to give energy throughout the body. But in order to catalyze this conversion, we have to put an energy source into this reaction, because you can't just go from a lower energy source, ADP, to a higher energy molecule, ATP, without some type of energy input. It's at this point that ATP synthase takes advantage of the proton gradient, which was being formed by complexes 1, 3, and 4. The protons will always want to flow down its gradient. That is to say, molecules in general like to flow from high energy states to low energy states to achieve equilibrium. So protons will flow from the intermembrane space down through ATP synthase back to the mitochondrial matrix, and when they do this, it is an energy input that catalyzes the conversion of ADP to ATP. That is how the energy is formed, and massive amounts of ATP are formed during that step because there's such a large proton gradient that can continuously flow downhill. Now, as those protons come across ATP synthase, they build back up on the mitochondrial matrix. So they're sitting in front of complexes 1, 3, and 4, ready to be pumped back up into the intermembrane space when 1, 3, and 4 get supercharged. As you can see, the cycle continues and the electron transport chain can continue to churn out ATP so long as NADH and FADH2 are being shuffled from the TCA cycle to the electron transport chain to continue the flow of protons. Now here's where we are at this point. That is how the electron transport chain works, and that's how electrons are shuffled along this membrane. Now, what's important for the purposes of exams, and what's very high yield to know, is what drugs and what molecules inhibit each of these steps. Now, I've drawn them here on the slide. Rotenone inhibits complex 1. Antimycin inhibits complex 3. Cyanide and carbon monoxide inhibit complex 4 and cytochrome C. Oligomycin inhibits ATP synthase. An uncoupling agent, such as 2,4-DNP, uncouples the proton gradient and inhibits the proton gradient's ability to pump protons down through ATP synthase. These are 5 electron transport chain inhibitors, or 5 inhibitors of oxidative phosphorylation that you absolutely need to memorize. Not only do you need to know them by name, but you need to know exactly where they inhibit the electron transport chain. Again, I'm including this here in this discussion because the purpose of the electron transport chain is to generate ATP. Now, we've already talked about glycolysis, about gluconeogenesis, about pyruvate metabolism, and about the TCA cycle. And at each point in these steps, you generate small amounts of ATP, but nothing compares to the massive amount of ATP generated in oxidative phosphorylation. Let's slow down, take a step back, and look at the big picture when we talk about how much ATP is generated at each step along the way. In glycolysis, you actually do form a small amount of ATP. Go back to the glycolysis video and look at the total net reaction. You do form 2 ATP, but you also form some NADH, and NADH can be used in the electron transport chain as you've seen today. So from the ATP itself, in glycolysis, you net 2 ATP, but from the NADH that can go on to be used in the electron transport chain, that can turn into 3 to 5 ATP. Because again, it's NADH and FADH2, which are the very rich substances used to pull electrons to go through the electron transport chain. In pyruvate metabolism, we formed some NADH, which can turn into 5 ATP if that NADH is used in the electron transport chain. In the TCA cycle, you do form some ATP, but it's a very small amount. It's a net of 2 ATP. But where the money happens is from the NADH and the FADH2 formed by the TCA cycle, which can go downstream and be used in the electron transport chain. So I'm talking about what's shown in red on the slide. Now the TCA cycle produces 6 NADH and 2 FADH2. In one spin of the TCA cycle, it produces 3 NADH and 1 FADH2, but the TCA cycle always spins twice. So you multiply those numbers by 2 to get 6 NADH formed and 2 FADH2 formed. Now over the years, biochemists have figured out that for each NADH molecule, you can form 2.5 ATPs. And for each FADH2 molecule, you can form 1.5 ATP. This is very high yield and it's worth memorizing. So looking at our equation, just from the 6 NADH formed in the TCA cycle and the 2 FADH2 formed in the TCA cycle, you can produce 15 and 3 ATPs respectively. Now looking from the top to bottom of this list, if you add everything up, one movement through glycolysis down to the electron transport chain can generate anywhere from 30 to 32 ATP. This is very high yield to know, and it just goes to show you that it's the oxidative phosphorylation step that produces the most amount of ATP, but that's only made possible by shuffling NADH and FADH2 from the TCA cycle and from other steps in biochemistry to oxidative phosphorylation to be used in the electron transport chain. That concludes today's video on oxidative phosphorylation.